recordings about Mexico, Jean and I. So we also began a collaboration on fragmentations. We gave 2 papers on these subjects. It was really a wonderful experience. Jean also offered me the opportunity of participate to defend jury thesis of some of his students. Some of them are the organizers now. It was the source of valuable conversations, friendships, and even a paper. Then I left fragmentations to other things, to random matrices in particular. But I keep an eye on one eye on those publications on fragmentations, etc. I was very interested. To respect the spirit of the conference, my talk will be related to one of the Jean's favorite objects, self-similar processes. It's a breakfast talk. There is no revolutionary novelty, just classical theorems on classical objects, but it was not unexpected, but it was very pleasant to prove these results with charming people like Nizar Demni, Marguerite Zani, and Maria Emilia Caballero in a stay in Mexico in 3 years ago. Okay, so let us begin with the talk. The source of this study is the defense of Marguerite Zani in 2000, where Marchior was in the jury and asked 5 questions. One of them was about Bessel clocks. Then he worked with Marguerite on one paper, and then the process began. Went on. So what is a PSSMP? For many people here, it's very, very well known, but I am obliged to define everything. So a positive self-similar Markov process with index alpha positive is a strong Markov process with paths in the square space and with some scaling property, so that the formula is here. Excuse me. Well, here. It's for every A and C. It's a property in distribution. Examples, of course, you have the square Bessel process, for instance, B1 square plus etc. plus BD square, where those B's are Brownian processes. Also, the modulus of continuity, the modulus of a multidimensional Cauchy process, etc. But we will see many examples in the following slides. So the main interest in those processes, the main tool in those processes, is in some sense to convert the scaling property, which is a multiplication property, into an additive property. And the additive notion is Levy process, of course. So every PSSMP never reaching 0 can be expressed as the exponential of a Levy process, not drifting to -infinity, time change. This is the key. Time change by the inverse of its exponential function. What is to say, formally, if you have a PSSMP, then you construct the integral from 0 to t ds over the xs alpha. You define its inverse, okay? And then you consider the process ct equal logarithm of x change of time change, then this process under QA does not depend on A and is a distribution of a Levy process starting from 0. From X to Xi, this is the way. The quantity is called the clock of X. In short, you have xt equal x0 exponential Xi, change of time. The change is defined from X. Conversely, if you start with the Levy process, you have to construct the PSSMP. So you define the exponential integral of the process, Cs. You fix also, of course, first you index alpha, you take the inverse process, and then you have xt, your PSSMP, equal exactly A exponential your Levy process. So there is a path from X to Xi and from Xi to X. Well, there is a huge literature on these subjects, in particular about the transition between X and Xi with the properties and the tools which are defined now are due to many people in many papers. So I give here a list of contributors. Of course, some of them are much more important than other ones, but everybody contribute to this field. In particular, there is a lot of examples. I will present some of them after, which are very interesting for their property, for some properties that I will give an idea here. So, first interesting thing is that when I gave the definition of the PSSMP, there was QA. So you start from A strictly positive. You cannot strictly, with this definition, start from 0. But it is possible to define Q0 as a limit as A tends to 0 of QA. There is also many papers. The notion is in particular developed in papers of Jean in Maria Emilia. So this interesting notion gives you the possibility of right here. Here, equality distribution without the initial dependence of the state. And then under this Q0, you have the law of X1 is exactly this quantity where appear the famous exponential integral of the Levy process, for which there is also a huge literature, in particular, nice papers of Jean, Yor, etc., which is called the perpetuity. So in some of the examples we will see after, there are explicit distribution for E infinite. For other examples, it's very implicit or very analytical. So this is Xi, X, and Q0. Now another guy will be present is the Ornstein-Uhlenbeck or generalized Ornstein-Uhlenbeck process. Also, it's probably Lamperti first will define this trick, but there are also many papers on this. Particular nice paper of Jean, which is very recent. So you have the process U of t exponential minus t over alpha x at time exponential of t. The generators of L of U and X are connected by this formula, which I will recall later. Because it's a very kind tool. And under Q0, defined just before, the process U is strictly stationary, Markovian ergodic, and its invariant measure is precisely the law of X1 under Q0, which I defined before by means of E infinite. So this is the very, very important process because we are able now to convert each question about X into a question about U, specifically when you are under Q0. So the tools also interesting are the Laplace exponent of our underlying Levy process. So it's defined here. We make some assumptions on this function psi, in particular that the domain of definition is an interval with 0 inside. And then we have some other properties. Capital property will be that C1 is integrable and the expectation is strictly positive, which is the very strong, but it allows to do everything in our context. And also that Xi is non-lattice. Well, before giving results, asymptotic results on the clock, I will give some interesting examples. The first one is the Bessel clock. So you take a Brownian motion with drift as the Levy process. Then X is the square Bessel of index 2, 1 plus nu. Your Levy, your Laplace exponent is 2m m plus nu, and E infinite as in inverse, which is twice a gamma of parameter nu. It's the toy model for everything here because there is behind the stochastic calculus and everything, you have several ways to prove something in this context. Then you have the Poissonian examples. So Poisson A, B, T is a sum of a Poissonian number with parameter A of variables distributed, exponentially distributed of parameter B. So you have different cases, particular the sawtooth process here. So they are more or less the same form. And in these three cases, the limiting variable exponential functional E infinite is completely, its distribution is completely known. Well, another example is very interesting, is the spectrally negative stable condition to stay positive. Then the Laplace exponent is a quotient of two gammas, gamma m plus alpha over gamma of m, and E infinite is the stable law parameter 1 over alpha. Then there is also a class which is known under the name of hypergeometrical stable process because the Levy measure of the underlying Levy process is a hypergeometric function. So it's complicated at the first sight, but in fact, there are many properties, and there are now several papers around Kyprianou and his friends, and also Pierre Paty on this process. In the particular case, alpha equal 1 and d equal 3, this is C of M is M plus 1 tangent MP over 2. This is, of course, when alpha equal 1, you have the modulus of Cauchy, multidimensional Cauchy process in this class, as many people remark. So the last example is the continuous branching process with immigration with index k between 0 and 1. The branching mechanism is this function, the immigration mechanism is this function, and C is also combination of noun function with the gamma function. For every examples in this list, we can check all the assumptions of the theorems I will give after, and this is why we consider them in this talk. So the first result is, of course, the law of large numbers. So to have an intuition of what is this law of large numbers, I will start with a remark in a paper of Jean and Yor, I suppose, is that the existence of Q0 is in fact connected with the asymptotic property of xt. That is to say, when you study t to the minus 1 over alpha xt when t tends to infinity, the asymptotic distribution is just connected to Q0. So, in fact, xt divided by t 1 over alpha has a limit, and then you can consider xt to the alpha as constant times t. So the integral you clock would be the integral of the function 1 over t. So it's log t. So the natural scaling of this clock would be log t. So this is exactly what I state here. Of course, it's not a discovering. It is already in the paper of Jean and Vandelin on stable windings a long time ago, not in this context, but in a very neighboring context. So what is the idea of proof? There is two results, under QA and under Q0. I will consider only the second. So just saying that U is ergodic. So you have the ergodic theorem for every function in L1 here. You have this law of large numbers for the process, Hochstein-Uhlenbeck process U. You change variables, then you have exactly your this limit, and then for the particular function x to the minus alpha, you get exactly your result. Here, the hypothesis was x as a mean, a positive Xi as a positive mean, your process is drifting to plus infinity, and then also not lattice. It's only this one. This ensures everything over U for U and E infinite. Okay, and this is the proof of 2. For the proof of 1, you have to take care of Markov property and the scaling in the definition of X. It's not so difficult. So I don't follow the chronological order. In fact, we prove large deviation between before fluctuations, but it's natural to go now in this logical order. Fluctuations, we prove the following result with Maria Emilia in Mexico 2 years ago. 2 years ago. Well, your clock is here. This is a variant because we don't begin with 0, but it's not very important. So this is the first order term for this clock, and then you scale with square root of log t, and then you get Brownian standard Brownian motion with p, which is the derivative, which is also in 0, which is also the mean of Xi1. The variance here, it's for people who are very familiar with renewal theory. It's a quantity with which is present in renewal theory. The variance divided by the mean to the power 3. Okay. No condition, no special condition on, no additional condition under Q0. And for the second assertion under QA, when A is strictly positive, it's not so easy. We need conditions. And in particular, these sufficient conditions are there. So let us give a sketch of proof of 1. It's an application of a theorem of Bhattacharya in 1982, which is a result with a play between the function you test, f, and some function g, for which f is the image of g by the generator of the process. Though, of course, here, y will be our Ornstein-Uhlenbeck process, which is stationary, ergodic, etc. And f will be our function with some centering, 1 over u to the alpha or 1 over alpha or something like that. And then everything works. So we have to look at our function and its pre-image here. And it appears that in this context, there is a family of very kind functions, the power functions, Fm, which satisfied this property. Why? Because you have this wonderful relation between the generator of X and the generator excuse me. So pardon. It is centered because F in the image of A. It is centered. If you integrate, it is centered. So for one, okay, though you have to apply it. So F is our 1 over x to the alpha, and then, or 1 over x if we choose alpha equal 1 for easier context. Then you have your h, you have your j, which is very easy to find. So it's not a miracle. We will see why, because this formula here, it's interesting. We will see one more time in the large deviation context after. It's not totally a miracle. Okay, so for the first, for the second result under QA, it's not so easy for 2. It's not, there is a typo there. For 2, the proof is more involved. We have to consider exponential ergodicity, which is not fulfilled in every examples, and some appropriate criterion. Everything ends well with our choice of parameter, except for the CBE process. We have considered the criteria which doesn't work, but we can consider another OU process recording that U is defined A minus T over K x to exponential of T. Here, we shift exponential T minus 1. This process for the CBE is another CBE with a change in the branching mechanism, and so we can manage the proof. So this is the fluctuations. Now, the large deviations. So we have, of course, need of some assumptions. Everything is okay since we already assume the good thing. So the theorem is the following. I didn't write on the form of principle of large deviation, just to see more precisely the thing, because there are question of domains. So, of course, the weight is 1 over log t. Your scaling of the clock is 1 over log t. So for x in the domain d delta bar, which is defined by the limiting of 1 over psi prime at the limiting point of the definition of your psi, then you find a rate function which is supremum of m minus x psi m. If you consider the dual function of psi, psi is the log Laplace here. You consider the dual psi star, and then its rate function is x psi star of 1 over x. People who work on large deviation found this weight function in some inverse problem, some renewal problem, first heating time of something, you can find this rate function. It's positive, convex, and which is unique minimum 0 at what is expected by the law of large numbers, that is to say, 1 over p. So what's the proof? The sketch of proof I will present is based on the Gertner-Ellis theorem. That is to say, you compute, if possible, the limiting log Laplace, and then you take the dual if everything works well. Here, there is a lemma, which is very important for the proof, is that the limit of the log Laplace, of the normalized log Laplace, you take the log Laplace, there are log t missing there. Okay. So the limiting value is L of t, where L is more or less the reciprocal function of psi. So with a change of sign. This is also present in some papers on reciprocal pairs with some works of Le Tac and his school. There are very interesting things, analytical, which can be considered with this duality relation. Well, how to prove this lemma? In fact, this is classical. It's a change of probability. So we change with a Girsanov here. So you take the Escher transform of the process, the Levy process. So if you consider some m, and then you consider the new exponent, Laplace exponent, you consider the Levy process with this exponent. And with this Levy process, with the mechanism I defined in the beginning, you take your xt as a PSSMP. Since there is this remark on generator here, and I didn't write the, the fundamental relation before Lx. So, owing to these fundamental relations, you can define this transformation, Escher transform for the Xi, then your PSSMP, then the law of this PSSMP. And then if you take the expectation under A of X minus psi of M integral 0 to t ds over xs, you fall on this expression. Now, due to the scaling property, you can transform this expectation in this form. So now n t tends to infinity. You take the log here. I have to remark that I drive everything in the case alpha equals 0, alpha equal 1. The index of self-similarity is equal 1, but there is a trick to convert PSSMP of index alpha to another PSSMP of index 1, and it's easy. So due to the scaling property, you have this expectation here. Taking the log, you have your principal, your first order term minus m log t plus constant plus here a over t tends to 0. It is possible to prove that this quantity is finite. Then taking now 1 over log, you find on your property there. So you have the limiting normalized log Laplace. I recall that there is log t missing. No, it's good. Excuse me, it's good. So, no, it's good. In the hypothesis of Gertner-Ellis are fulfilled. The functions are steep in these examples. So, for many of our examples, the rate functions are explicit. Here are the results. For the other ones, it's not explicit, but it can be drawn. It's not very difficult. It's implicit relation, but perfectly managing. It is perfect. It is easy to manage these rate functions. So, some comments. First, it seems to be a miracle that the function fm, the powers ends very well. And why this appear in this proof? The second comment could be, okay, for the law of large numbers and the fluctuations, we use the underlying Ornstein-Uhlenbeck process and its wonderful properties of stability, of stationarity, etc. Why not for the LDP? Of course, it's possible to begin the work for the Ornstein-Uhlenbeck with some properties, generalized Ornstein-Uhlenbeck. Then you have LDP for the occupation measure and even for the process. And of course, your clock written by means of the Ornstein-Uhlenbeck is in fact a normalized, well, there is no 1 over log t here. 1 over log t here, there is some typos. 1 over log t here equal 1 over log t here equal 1 over log t here. Okay, so this occupation measure gives large deviations, level 2 large deviations, and then why not apply a contraction? But the issue is that f minus alpha, that is to say, is of course not continuous. So it's not possible. In fact, we could be tempted to try to, to manage a computation, even if it's not, even if we don't satisfy the continuity. What happens if we suppose that we have the right to apply the contraction? So it's possible. In the special case of the Bessel clock, of course, LU is very well defined. It's the Laguerre semigroup, so the Laguerre infinitesimal generator. Mu is the key square dimension D, and the rate function is this for the occupation measure. That is to say, probability that 1 over log t integral 0 to t delta u, etc. With h, which is exactly the square root of the Radon-Nikodym derivative. So you can contract, say, I take the infimum of this rate function over those measure mu such that they have a precise defined before clock. So the value of the clock would be y, and then if you take Lagrange multipliers, you see that there are one and only one solution, which is precisely x to the m. So it's not a miracle. This is the optimal occupation measure to which the value y of the clock. Even we can go further to the level 3 to see what is the process, and we could fall on the process I defined before with the Girsanov property. So thanks for your attention and happy birthday, Jean.
Thank you very much for the nice talk. And are there questions?
Thank you, Alain. It's a question about your central limit theorem. So you the assumption for the Ornstein-Uhlenbeck process to be ergodic is actually only that the Levy process has a finite positive mean. It is sufficient, but you are assuming much more. You are assuming that the Laplace exponent is finite on some neighborhood of 0.
Yeah.
And I was wondering whether this is something which you really need to get the central limit theorem.
No, in fact, it's not. It's not necessary. I put the assumptions in the first slide because I was in my mind large deviations, but it's not necessary for the. Okay. We don't use it for fluctuations, of course.
And would it be possible, in your opinion, to get stable Levy processes with only positive jumps in the limit in some extreme cases?
It's a very good question. I don't know. It's possible to consider, but I don't have any idea of what could be the hypothesis to reach this conclusion, but it's very interesting.
Any other question? Maybe from the chat? Or? Okay, then we can thank the speaker again.
J'ai une question, j'ai posé de la poser.
Ah, pourquoi? Ah, pardon. Ah oui, j'ai le micro. Il faut éteindre ça, je suppose. Non, voilà.